So this afternoon is kind of the first time. I mean, the first time I made this presentation. So we'll see how it goes. But since a couple of years, we have become interested in one particular topic. I mean, among other things we saw this morning, which is explainability of graph neural networks. I maybe also explain why, but basically we ended up in an European project, sort of an European project, that was about explainability in general in deep learning when applied to scientific problems. And so we started thinking a lot about explainability, and we kind of started to apply it in graph neural network because there are lots of interesting use cases. Basically, as you saw, there are dozens of use cases in medicine, for example, or in energy grids, etc. So there are a lot of situations, scenarios where it's critical that you can explain why something is happening. This presentation is a little bit strange because, I mean, there's explainability in graph neural networks, but there is also explainability in general in artificial intelligence, and it's hard to disentangle the two. So the presentation itself is, we talk a little bit about the general problem of explainability from, let's say, a modern point of view. Then I'll show you how you can actually apply classical. If you've ever heard about explainability or read something about explainability, I'll show you some classical ways of performing explainability and how you can do that on graph neural networks. And finally, I'll show you something, let's say, more tailored for graph neural networks and also something of our own research group. There's actually a notebook at the end. And so I hope that this will take, let's say, maybe a little bit more of the time slot. And the other half, I will just load up the notebook and show you how you can implement graph neural network in practice. And some interesting, let's say, bits to know if you come from a classical PyTorch work. And also a little bit about explaining how explainers work in practice, which assume I know how to use a Mac, but that's a problem for later. So how many of you already know about explainable AI? I try again. So how many of you know about explainable artificial intelligence in general? Very few. Okay, that's. I don't understand if this is a hands up, hands down. Okay. So half. Okay, that's good because that's exactly how the presentation is tailored. So this is again, if you tell me we're talking about buzzword, graph neural networks is huge, but explainable AI is absolutely out of let's say any rationality. Let's say so. It's become a topic that because we talk about explainability, we're talking about explaining things, we're talking about trust. So it has become an immense topic in governments, regulators, etc. So it's gone way beyond, in my opinion, its real usefulness. But anyway, I'll try to give you a kind of an overview. So first of all, what's explainable AI? There's this very nice acronym, SSIE. And I spent lots of time thinking about the references to put in my slides. So let's say every time there is a reference, I think it's something that you should probably read if you're interested. This is a decent guide, decent introduction to the topic, but basically it's a broad field which says concerned with developing tools and models that somehow should allow you to understand what the model is doing, and as such also increase what they call the trustworthiness, trust in that model. So basically the biggest problem you face whenever you deploy a deep learning model is that people tell you, okay, that's very nice, but why? Why is this user a bot, for example? Why is this molecule a good antibiotic? Why is this person denied a loan, etc., etc. And every time you do that, they want somehow to understand what's going on. So if you can do that, you will increase the trust of people that are using those models, but you also learn, let's say, something about the model itself. And there's a sort of a common fault to dichotomy, why I'm writing these things. But basically, the more complicated your model, the harder it is to interpret. So there is here, so that there are what we call what I'm calling here intrinsically interpretable models. So there are some models which are very, very easy to interpret, but typically they are also the models that don't really work when you need them. And then there are models that are incredibly powerful and typically deep networks, but kind of hard to explain. And so you will see stuff like this, where basically there's a trade-off between sort of predictive power and explainability. And the most explainable method, in my opinion, is just a linear regression, because in a linear regression, every feature has a weight associated to the feature. So by looking at the weight, you can understand the importance of the feature. So if a feature has a weight of 0, that's completely useless. If a feature has an incredibly large weight, it's an incredibly strong predictor, and that's it. That's their entire economics field based on this insight. And then you have decision trees, where basically you can follow the branches of the tree to see why the model is making that decision, and then on top you have the neural network, where you have absolutely no idea what's going on. Now, the people have, just to tell you, explainability has a long history, let's say, but recently people have become quite disappointed with explainability. I mean, I'll try to tell you why, but basically there's an immense amount of explainable methods, and it's not very clear what are the theoretical guarantees of most of these methods. And also, most importantly, they've been oversold. So basically, too many vendors have taken the idea of explainable AI to try to sell deep learning method where they shouldn't have. For example, if you're trying to sell a technique that diagnoses a certain, I don't know, X-ray, for example, and you try to sell it, the other guy doesn't want it because it's a black box, and you say, hey, no, look, but mine black box is an explainable black box. So, I mean, you can trust me, and whole host of problem appears. So that's created something of a problematic. I do have my own philosophy on that, in the sense that for me, there are basically, I see that there are two main end users, let's say, of explainable AI. Okay, there are two main groups of people that want to use explainable AI. And the first one are you, in the sense that explainable AI is, I mean, for me, it's a very useful tool for debugging, basically. So I'm implementing a graph neural network, for example. I see that it sort of works in terms of accuracy, but then I will try to understand a little bit more about what is going on. So I am someone who knows a lot about this. I also know a lot about explainable techniques. And I think they are pretty useful. At least to me, they are useful, typically. So if you are what I'm calling here a practitioner, explainable AI is quite useful. So you will see that you can gain a lot of insights if you know what is going on. Then there are real end users. So for example, clinicians. And in that case, I would say it's still an open problem. So it's very, very hard to sell something to a clinician, to a doctor, et cetera, even if it's explainable, that is really, really explainable and useful. Mostly, again, because different methods may disagree. So we'll see there are dozens of explainability techniques, and they all give you different results. So what's the actual explanation then? It's not really clear. And also they dock typically on some real strong principles, but we'll see a little bit more about that. But just to tell you, there's a lot of, right now, I won't say hate, but disappointment in explainability in some scenarios. But I don't think we should care about, because for me, I'm also the one who's using the explainability techniques. For me, they're just, I like to call them debugging tools. So they're just methods that are very useful to see what's going on inside my neural network. Here's an example of this disappointment. Zachary Lipton is a very famous researcher at Carnegie Mellon University, and there was this viral tweet saying, we should be far more scared upon hearing that someone is deploying a explainable technique than not. Because basically, it's being used a lot as a marketing tool when it's not as strong as they sell it, basically. But again, this was my own introduction. Now, what's This is a nice book. If you want, it's independently published, but there's lots of categories, let's say, of explainability techniques. And here I'm putting 3 of them, and we'll focus on one specific category for each, basically. But how do you go beyond the trade-off I showed you before? So there are methods that are very powerful, but black box, and methods that are quite interpretable, but they lack power, let's say. So you cannot apply to complicated scenarios like our scenario. Like if you have a graph, you need to use a graph neural networks. There isn't a lot more than you can do. And the key point is to go from what is called here global explanation to a local explanation. So again, before when I told you about linear regression, in linear regression, every weight is associated to a certain feature. And that's a global explanation. So I know that a feature is globally important for my problem, or it's useless for my problem. But what we care about typically are local explanations, which are more interesting in the sense a local explanation says, okay, I don't want to know how the neural networks works in general. I actually want to know why it works like this for this specific input. So if I have this specific X-ray, for example, and I'm getting a certain classification, I want to know why, but I want to know why only that classification has been made. And this is quite interesting because if you look at this figure here, you see those are classes, they are highly nonlinear, but if you look at a specific point, its classification probably only depends on a small number of points. I mean, we might be able to decide why this is a purple circle by not looking at the entire network, the entire data set, the entire everything, but only on a simplified model, let's say, that describes how the model is working in that neighborhood. So we'll focus on local explanations here. This global explanation is completely open research field. So if you find a way that allows you to get a global explanation, easy, interpretable explanation for a generic deep neural network, that's completely open, let's say. Local explanation, there's things we can do as we'll see. Then there are methods that are model agnostic or model specific. So some methods will only work for a certain type of model. Some methods will work for any kind of model. We'll see a mixture of the two, actually. But then the most important thing, we'll have something to say about this, is what's an explanation? So when I'm saying I'm explaining a certain prediction, then we need to decide what's the explanation. Is it a text? Is it something else? And most methods actually will see that, but they define the explanation as a part of the input that was highly relevant for the prediction. That's the simplest thing you can do. But we'll see other options. Let's say, for example, you could say, okay, I want a sentence describing the prediction, or I will say something else. I want to know which point in my training set was the most important, or anything else. So basically, whenever you're saying explainability, this is the key point. So you need to decide if it's a local or global explanation, and if it's a local or global, what's the explanation? What is the format of the explanation that you want? I had a picture about this. And I actually stole this from the MATLAB website, and this was a real surprise. So you see, you have a model. The model is highly nonlinear. It's a simple binary classifier. What happened is that here at this point, for example, this yellow point, if we only look at the neighborhood of this yellow point, you can probably linearize that. So you can look at the behavior of the deep neural network only in a very short neighborhood. So you can build, for example, a linear model on top of that, and then you can understand this simplified model to see what are the driving factors behind only this particular prediction. This is a very, very famous method called line. But just to give you an idea. Now, we're not talking about explainability in general, we're talking about explainability for graph neural networks. So given this, we'll focus on local explanations, and in particular we'll focus on one particular type of predictions where the prediction itself is given by the part of the graph that was the most responsible for the prediction itself. So if I'm telling you, okay, this user is a bot, the explanation is the part of the graph that had the biggest impact. For example, if it's connected to other bots, then maybe that will be the explanation, or something else. So you see here we have, this is taken from one particular paper that we'll see called GNN Explainer. It's a little bit complicated, but I mean, I think you can understand it. There's a graph, there's some classification on top of the graph. And basically when I say, okay, here's a point, here's another point, give me their explanations, the method should return me some small subgraphs that are relevant. So that this should be the part of the graph that the model has used the most to make the prediction. So this, when you hear about explainability, this is the framework for 90% of the works on explainability. It's easier if you think about images, maybe. In an image, an explanation in this case, in this form, is a highlight of the salient part of the image. That's the same, but applied to a graph. But it's much harder than in an image because, you see, visualizing these graphs is not very trivial. By the way, what I discussed this morning was, let's say, established literature. This is ongoing literature. So this is a very recent, very open problem. So anything I say can become completely outdated next year. Is this clear? Do you have any? Is an excuse for thinking? I mean, it looks like a very simple problem, but actually we'll see we have dozens of solutions. So even if now we have categorized quite precisely what our problem is, and you see it can have a huge amount of implications. So if I tell you that a certain molecule is has a certain property, for example, it's a good antibiotic, then I want to know, okay, why is it a good? What part of the molecule are the most significant for that? For example, if it solvable, soluble in water, right? It could be that there is a certain, I don't know, triplet or pair of atoms that give the molecule that property. So that's kind of interesting. And in mathematical terms this is the problem. So on the right, I have my neural network, which is making a certain prediction. So that could be a prediction on a node, or it can be a prediction on an edge, or it can be a prediction on the entire graph. That depends on the problem. And I want to find binary masks. So I will have typically a mask on the feature and a mask on the edges, on the connectivity of the graph, such that these masks should be small as possible, the smallest possible number of ones, but the prediction should be consistent. That's more or less the formulation of the problem. We'll see that depending on the way we find these masks and the property we impose on them, you can have very different algorithms and methods. So again, original prediction, masked prediction, where this is a mask on the features. So I'm saying don't use that feature, zero the feature, and this is a mask on the edges. So I'm removing edges, basically. So that if you see here, all the edges here that don't appear here have been masked out in this MA mask. Yes, I'd like to mention something here, which is that we actually still have a huge problem. So I will show you lots of methods, many different methods that you can use to explain in this formulation a graph neural network. if you try to use them, you will immediately face a problem which is still open, which is that at some point, if you have 10 different explanation methods, you need to decide which method is the better one. And in machine learning, you would do like cross-validation or things like that. For example, if you need to decide if you need 10 layers or 11 layers, or if a ResNet is better than an efficient net, you just fine-tune everything. Here, it's not so easy because typically when you're trying to explain things, you don't have a ground truth. So in your data set, you don't know the perfect explanation. And even if you know the perfect explanation, you also need to define good metrics about the explainability. This is a nice paper that introduces this. But you see, so you have, in order to decide which explanation method is best, you need to have a data set where somehow you have the perfect explanation. And this is really, really, really hard. So there are only, we'll see that most results that we have either artificial data, where of course you know the ground truth because you generated the data, or you have very simple biological molecular data sets where you know that there are a small number of compounds like carbon rings that give rise to a certain property. So this is really a huge problem. And also deciding when a certain explanation is good is another problem. So you can, basically you need to see that it keeps the original prediction consistent. It must be stable if you remove a certain number of edges, etc., etc. So there are many, many different metrics that you want to. So this slide is here to tell you that I will show you a few explainability techniques, but I won't be able to tell you, okay, this one is absolutely the best metric for your problem, because it's impossible, basically. And also, if you want to do research, finding data sets with an explainability ground truth would be incredibly useful. Okay, I will show you three methods, basically, 3 classes or 4 classes, or too many slides. But simplest thing you can do is to say, okay, this is very similar to classical explainable AI. Explainable AI was born mostly in the field of computer vision. And in the field of computer vision, they found many, many different techniques. So the first thing we could do is say, okay, let's try taking classical explainability algorithms that we know about for images and just adapt them to the use case of graph neural networks. And it kind of works, and we'll see a couple of them. Then the second thing you can say is, okay, they don't work as well as I'd like. Let's try defining new methods that are tailored for graph neural networks, and that's the second part. I think this is interesting because the methods we see here in this section were born in the computer vision field. So you can actually apply them, actually you will find them applied on images most of the time. So if you have an computer vision problem, for example, those are methods you can apply, and sometimes they're useful. And they're called attribution techniques. So attribution techniques means that we want to attribute a certain relevance to every element in my input. In an image, they will be pixels. In the graph, they will be edges and features. And I'm calling them classic because, again, they come from a different, when people talk about explainability, explainable AI, those are the methods they think of. So let's really start from the beginning. So one of the first explainable, remember that the big push in deep learning came around 2012. AlexNet, ImageNet, etc. So after 2012, everyone started working on deep neural networks, more or less. So it's not surprising that the first works that say, okay, but what's going on here? What's happening inside convolutional neural networks? Why do they work so well? Came a little bit later. So we are in 2014, and people started talking about, okay, let's try to understand what's going on inside convolutional neural networks. And that's more or less when modern explainable AI was born. And this paper in particular had a very nice technique called occlusion, which is a model agnostic techniques to try to find those masks, basically. Now here I'm describing it for images, but it should be pretty easy to understand how you can apply that to graph. So the idea is that you take the unit inside the neural network which has the strongest activation. So the idea is that the layer just before the final decision, you will have a certain number of units, and they will be differently activated. And the strongest activation in principle is the one that will contribute the most to your prediction. Then you slide a gray box over this was the input image basically, and you record what is happening to the output. So if what am I saying is if I'm saying this is a water bottle and this is the entire image, then if I put a gray box here, in theory the network should be unable to recognize the water bottle anymore, and so I should be able to say, okay, this is a very relevant part of the input image. And if I plot that, that should give me enough information. So here's an example from the 2014 paper. Again, image. We will jump a little bit between images and graphs in this part of the presentation. So those are, okay, this is a dog, this is a car wheel, and this is another dog. You might know that ImageNet has an absurd amount of dog breeds, because at the time they were considered incredibly difficult. And you see what happened is that I have a gray box and I slide the gray box across the image. And maybe this is the most interesting part. So this is the final classification, and the colors are the probability of here the most probable class, and here the probability of the correct class. So if you look here, this is quite easy to interpret actually. So by the way, how do you read that? So you see here, you put the gray box here, then you see what happens to the prediction. And so here in this pixel, which is the center of this gray box, you put for example, the class which is predicted, or the probability of the correct class, or the strongest feature map, etc., etc. I mean, any quantity related to that. And you slide the gray box and you record everything. And this is quite interesting because you see, if I put the gray box here, which is here, then the network will start predicting tennis ball. Or if I move it around here, it will incorrectly start to assign different dog breeds, because maybe it cannot recognize the dog breed anymore. So you see, this is quite helpful, because basically it's saying, okay, this part of the image, which corresponds to the face of the dog, is the most interesting one. So it's for me, that's the actual explanation of this image. They're nice. I mean, it takes a while to understand how to read them, but they give you quite a lot of information, and they're very simple to implement. It takes you, I don't know, 10 minutes to implement these kind of things. And turns out I tried to see if anybody had applied this to graphs, but nobody had, and I didn't have time to make an example. But this would be pretty easy to apply to a graph neural network, because instead of sliding across instead of masking the image, you can just mask every edge in turn and see what happens. And you should be able to get a saliency map, but again, didn't found anyone. So if you want to try, you'll be the first one. Also, not a lot of people somehow use occlusion. Now, this is way more famous. So it came more or less concurrently to the previous paper, and it kickstarted probably the most famous explainable AI technique, which are called saliency maps. So saliency map is a way to find the masks that I was telling you about before by looking at the gradient of the model. So the idea is that the gradient of the model, so if I take an output and I compute the gradient should tell me basically the gradient with respect to the input, okay, not with respect to the parameters. The gradient will tell me, okay, if I change a little, if I make an infinitesimal change to this input, I will have that infinitesimal change in my output, which is kind of what we're looking at. So in theory, if I modify the important pixels, I should modify the output a lot. If I modify the, I don't know, background, I shouldn't change the output too much. And a saliency map is quite simple. So imagine that this is F. Fi is the class that I'm predicting. X is the image in this case. I just take the partial derivatives with respect to every pixel. And this will have the same dimensionality as the original image. I'm taking the max over the channels, and that's my saliency map. Again, this is one line code in PyTorch because you're just taking a derivative with respect to the input as compared to respect to the weights. And it's crazily popular. So 90% of what you'll see on internet when they say, hey, look, I made an explainable application, they're using some variation of saliency maps. Because they're incredibly easy to compute, because this can be done using the same automatic differentiation mechanism that you use to actually optimize the deep neural networks. And this is the kind of results you get. So you take the image, you just compute this, you just compute this, again, one line code, and you plot it. You plot the absolute value, and in principle, it should highlight the salient regions of the image. And unsurprisingly, this was also the first method that people tried in graph neural networks. So there's a little bit of time in between, but I told you that graph convolutional networks was from 2016, 2017. You see 2 years of time frame, like for convolutional networks, we get to 2019, where graph neural networks started having lots of application, and so people started to say, okay, but now I need to understand why they're making these predictions. And this paper in particular said, okay, let's try common explainability techniques and see what happens. And it's pretty easy to replicate saliency maps for graphs, because what you do basically is you do this almost the same exact thing. I'm missing some absolute values, sorry. But instead of taking the gradient with respect to the input, you take the gradient with respect to the adjacency matrix. So this will tell me if I make a small change to an edge, what will happen to my prediction? And in theory, the strongest connections should be the one that have the highest impact. So if I take the saliency map and I only take the edges which have the highest activation, and I plot that subgraph, I should be able to get a kind of saliency map for the graph. I mean, you can do the same and you get the input feature, the input saliency map, but I'm focusing on the adjacency saliency map. And that's an example which I completely forgot, by the way. That's the kind of thing you get. So this is the input. Oh, no, sorry, no, so there's no explanation yet. But basically, this is the input, this is what you like to get, and this is the prediction of the neural network. Then you can just take a particular node, which I lost. Here, this should be node 11. And these are all the edges in your graph. And in principle, if you plot the saliency map, this should tell you which edges are the most important. And this is maybe you don't see that here, but there's a couple of connections here in very light gray, but basically you make that computation, you plot the resulting subgraph, and that's supposed to be your explanation. You can already immediately understand from here that, I mean, in images, you see, you get kind of, I mean, even if the method is horrible, you get a decent result. Like here, you can mostly, if he tells you that this is a dog, you can say, okay, I'm happy about this result because I can see the dog, right? So you're pretty confident that it's working as you expected. Even if the saliency map is not particularly well made, it has a lot of additional pixels, etc. In graphs, it's harder because if you have a graph like this, I will give you a big subgraph here, and understanding it, it's not as easy and as immediate as with images. Now let's take a step back. These basic saliency maps, they were proposed in 2013, 2014, but they very soon became updated because they have a lot of, they have many disadvantages that balance the fact that they are very simple to compute. And in particular, there are three problems here, but the first one is that they're very unstable. So if you try to compute the saliency map, then you modify a little bit the image and you compute again the saliency map will change a lot because that gradient is very highly unstable with respect to the input. They tend not to be well localized in the sense that if you try that on an image, you will have a lot of pixels that are highlighted, the single pixels that are not really relevant. And in a graph, this is an immense problem because every edge that you plot will make visualizing the figure harder. And also they have absolutely no formal guarantees. So you try the saliency map and you hope for the best. And this drove a lot of research in explainable AI. So lots of researchers have tried to face these three problems to define sort of advanced saliency maps that are stable, are localized, and have a little bit of formal guarantees. In particular, one formal guarantee that you want is this so-called sensitivity. So basically, if you have two images and they have two different predictions, and they only change for one pixel, then by definition, that pixel should be part of the explanation. That's the property which is called sensitivity. So if I have a social network and I'm classified as a verified user, then I make a single connection. So I say, okay, let's be friends. And now I become a bot for the model. Then this connection should be part of the explanation of my being a bot. And again, this is called sensitivity. And a saliency map is guaranteed not necessarily to have sensitivity. So one famous method that can recover sensitivity, I'm not going in the theoretical part, you can read the paper if you want, but this is a simple variation of a saliency map that is also guaranteed to have that property, is called an integrated gradient. It looks scary, but it's quite easy to read actually. So let's think about images first. So So first of all, what is here is the saliency map. It's the partial derivative of the function here with respect to the adjacency, but it could be with respect to the image. So that's a saliency map. The only difference is that instead of computing the saliency map by itself, you compute the saliency map across a path. So this integral here represents a path. And in the computer vision, it's easier. So the path goes from the black image to the image you're trying to explain. So the idea is that you start from a black image and you see the explanation. Then you quickly move towards the actual image and you integrate all the explanation across this path. So in this integration, basically only the really relevant bits should be kept. So how do we read that? So imagine that this is the image, this is the empty image, and this is a coefficient that goes from 0 to 1. So this is the path that goes from the empty image here to the actual image. So for alpha equal to 1, you are only looking at the original image, and from alpha equal to 0, you're only looking at the black image. And basically, you move alpha from 0 to 1, and every time you record the saliency map, and then you just average them out. It looks scary, but if you do that using, if you take fixed intervals instead of the integral, this is 5 lines of code. You just move from 0 to 1, add, make that linear combination, and compute the saliency map. Okay. That's for images. If you want to do that for graphs, you can do that easily. You just say, okay, I'm moving from the empty graph, so no connections, to my own graph. So for alpha equal to 0, you will have no connections. With alpha equal to 1, you will be back to your original adjacency matrix, and you just integrate all the different explanations. Of course, there's an integral here. In practice, you would just discretize the interval here and just average all the, like for 0, alpha equals 0, 1, alpha equals 0, 2, alpha equals 0, 3, etc. And it kind of works well. So this was the paper that introduced a lot of metrics. And this kind of strategy kind of works decently. So here you have how do you read it? So these are singular. By the way, those are the only two data sets that we have for which we can evaluate the goodness of an explanation. So on the bottom, you have artificial data sets. So for example, BA shapes and BA community and tree grid, they are data sets where there is a certain, for example, here, a certain, sorry, there's none. So you see here, you classify this graph depending on the fact that it's a tree or not. If it's a tree or if it's a grid, or if it has a grid. So the explanation is the grid, if it's a grid. Or here, you classify it depending on whether there is a certain shape or not. So the explanation is the shape. So a good explanation should be able to highlight the shape, but also remove everything else. On the top, instead, you have a data set which is called mutagenicity, which is a data set where basically you're trying to predict if a certain molecule will react in a certain fashion. And you know that the reaction will depend on a certain number of elements, like this ring here, or this triplet here, or a certain number of alkaloids, etc. So those are the only two data sets where you can actually make some comparison. And this paper evaluated a number of attribution techniques, and this integrated gradient was decent.
Can I ask a question? In the previous slide, I couldn't understand the A0.
So in computer vision, this would be, let's say, the image and the empty image. An empty image is a black image. Here we have the original adjacency matrix and the empty adjacency matrix. The empty adjacency matrix is just a diagonal matrix where you have absolutely no connections in your graph.
Only self-loops.
Only self-loops. Because if you also, and sometimes if you also remove self-loops, the network doesn't even work anymore because you have absolutely no more messages.
I see.
Okay, so I mean, this was half enough, let's say. So the saliency maps and integrated gradients are very used also for images. They are kind of useful for graphs. So I linked here a few papers that were trying to do that, but eventually they found out they didn't work so well for this kind of problems because so it's fundamental that the resulting subgraph is really small. So the point is that for an image, you plot a saliency map, and if the saliency map is not that good, you don't care so much because you can still visualize it easily. So a saliency map is an image, and we are pretty good at visualizing images. Here, the saliency map is a graph. So if the graph is not small enough and it's large, it's really impossible to really understand it and visualize it. So basically, almost every method that was proposed in the literature for images didn't really care that the saliency map was as small as possible, like counting the actual number of pixels, because that was not a huge problem. In graph, it is a huge problem. So there were a few methods starting from 2019 that try to say, okay, let's define specific explainability techniques that allows me to get a saliency map, a mask over the graph, which is also as small as possible, as precise as possible, okay, as concise as possible. And the most the seminal one, let's say, so the one that everybody has been following recently, is called this GNN explainer method, which is actually simple. So the idea is that all these masks that we saw here are just like, you take the definition here, you apply the definition, and you get your saliency map. The idea of GNN explainer is that instead of doing that, you actually try to optimize them. So you actually run an optimization loop to get the best possible masks. And in particular, you run an optimization loops with these two constraints. So the first constraint is that the masked prediction should be the same as the original prediction. So the mask should not change the actual prediction. And the mask should be as small as possible. So you can just use some L1 regularization, so the absolute value of the weights inside the mask, to keep them as small as possible. And you get this kind of cost function. So you get this cost function, you optimize it using standard gradient descent techniques, and that the solution is your explanation. So you have, so the mask here is the argument of the minimum of this three-way cost function, which is sort of simple to read. So the first block, the blue one, is a cross entropy between the original prediction and the masked prediction. So the two predictions should be as similar as possible. So you don't want that applying your prediction changes applying your mask changes the prediction. Yes.
So this is using an optimization algorithm. But in the previous method we talked about
No, the previous methods are just you apply the saliency map, the integrated gradient have a definition, you apply the definition and you get the saliency map, and then you plot it.
do we like just look at different masks and see like by hand?
I mean, there are similar methods also for images, but they are not very common. It's much more common to just, they're images. So if you have 10, you just look at them and see which one is better. In graph, recently it's become more common to do this because you really want them to be as small as possible. So this is a standard cross entropy. So you're saying my prediction, original prediction, and the masked prediction should be as close as possible. I don't want to change the actual prediction. Then I want the mask to be small. And I mean, maybe you know that, maybe not, but if you want something to be as sparse as possible, you can do that by adding an L1 regularization term, the loss, this is just the sum of the absolute values. And the sum of the absolute values will tend to drive the mask to be sparser. And okay, this is technical, but you can also add an additional term, which is the entropy of the mask, because minimizing the entropy of the mask will make the mask go to spiked values. So basically what happens is that you don't want like 0.4 in the mask, because is it inside the mask, is it outside the mask? You want to be as close as possible either to 0 or to 1, and you can do that by also regularizing the entropy of the mask. This is easy to do. I mean, you write out the optimization problem, you can use any Adam or any other optimization algorithm, you run a few loops, and you get the mask and you visualize it. But I would say this was the first application that got really good results, even in synthetic dataset. So again, this is the community artificial dataset, the shape artificial dataset, the mutagenicity dataset, and I honestly don't remember this one, but it's a question answering dataset from Reddit. This is a standard saliency map. This is a slightly more sophisticated saliency map, and this was GNN explainer, and in general, results tended to be a little bit better and a little bit more readable. And you see here, for example, you actually have the circle, here you have the actual grid, the ring of carbon atoms. How much better? Every paper will tell you a different story, but I mean, generally better than the saliency maps. I'm skipping this one if you want to read it, but basically you can make this a little bit more sophisticated by so what happens is that, for example, what happens if you want to explain 10 different graphs? You need to run this for 10 different optimization loops. So you need to optimize the mask for the first graph, the mask for the second graph, etc., etc. And it sort of takes a lot of time. A slightly different variant is this parameterized graph explainer, where basically the probability, what happens here is so graph inputs, and the probability that an edge is inside the explanation or not is given by another neural network, parametric neural network, that learns to say, okay, here's part of the explanation, this is not part of the explanation, etc., etc. And this is slightly better if you want to make explanation for thousands of graphs. But again, you can read the paper, it's written pretty decently. And here's a sort of a random list of interesting papers. They almost all came out very, very recently. And so this is really a field that was born a couple of years ago. But if you're curious, if you know line, there is a graph variant of line that you can try to apply. There are a small amount of work that try to find different subgraphs that generalize across the different graphs. And there's a whole class of interpretability method called Shipley values that are some game theoretic base. Let's say there's extensions for graphs, and well, I would say this is a kind of a decently complete bibliography if you want to read about explainability in graph neural networks. I'm skipping this. But basically, I wanted to show you a couple of things we are working on in terms of explainability. So this was, let's say, established explainability techniques. So if you GNN explainer and PG explainer are the two most famous explainers for graph neural networks, probably. Now I wanted to show you a couple of things we were trying on in our laboratory. But actually, the first one, we still don't have results, so we still I can discuss it generally, let's say, but if you're interested, you should wait a little bit. But basically, there's some somewhere. Hello? Okay, I don't know what. But what happened is that, again, we were in this sort of kind of European project, and we were trying to apply these explainability techniques to a number of scientific use cases. And one use case was about segmentation, semantic segmentation in images. So semantic segmentation is something like this. So you have an image and you want to segment every pixel to see what it belongs to. And in that particular case, it was a clinical semantic segmentation data set. So you want to know where tumors and cancers and everything else is inside an image. And we sort of found out that, I mean, we had an issue that people came to me and said, okay, but what's the saliency map of a semantic segmentation problem? I mean, the segmentation itself is kind of self-interpretable. So can I also make a saliency map on top of that? Because, I mean, for them, everything in the explainability world, let's say, is linked in some way or another to some kind of saliency maps. So they had a problem because they had promised to do something explainable, but they didn't know how to do a saliency map on top of a semantic map. And so I proposed some nice methods that I was studying that basically try to frame the explanation not in terms of saliency map, so not in terms of, okay, which features are the most important, but in terms of which points in my training set were the most important. So my idea was that, okay, if, for example, I have here, maybe I found out that the car is poorly segmented. What's the explanation for that? Maybe it's not in the image itself. So maybe there is some other image in my training set where a similar car has been poorly segmented. And that's actually a good explanation. And so this alternative class of explainers try to provide an explanation by basically finding the influence that every training point is having on my actual prediction. So if I misclassify a training point, then I see a similar point, I make a poor prediction, the explanation is that I had a misclassification. But also, if I see a dog, probably the explanation is that in the training set there were similar dogs. So this is sort of useful, but it's also pretty hard because I need to compute this influence, and this influence is through the training process, so it's highly nonlinear. And again, we were building on a paper called gradient tracing, but I leave it here because I don't have the results for the graph part. But basically, we're trying to define methods where I give you a certain prediction, and the explanation, for example, for a protein would be similar proteins, or proteins that have similar characteristics, which is pretty good for clinicians or people investigating that. And this is completely nascent field, let's say. So the first methods here are from 2-3 years ago. There are still huge problems in explainability in general, but also explainability in graphs. And here are 3 problems that I think are interesting. So the first one is that, so the second one, again, there are no data sets. So if you can think of a data set where you have an actual ground truth explanation, that would be very helpful because that would give us a way to find the best explainability methods. And also, I have not gone in depth in this, but even if you have the data set, you can define the goodness of an explanation in many, many different ways, and they tend to differ between them, faithfulness, accuracy, so it's not easy. I wanted to focus a little bit on the first challenge here, because this is a research line we have been pushing a lot recently. But I think that a very big issue about many explainability models is that they typically are added only at the end. So you train a model and then you say, okay, now I want to explain it. But you have no guarantees that you will get a good explanation. And this is an issue if your problem is critical in the sense that you need that explanation. You have no way of forcing that the explanation is good. You can just say, okay, like here I train a graph neural network, I promise an explanation to my client. And the only thing I can do is, okay, let me try GNN explainer. Let me try SSIE and CMAP. Let me try integrated gradients and see what happens. But you have no guarantees that these explanation methods will actually work well. And this, in my opinion, this will be one of the most interesting research lines in the future, because if your problem requires good explanation, you want your training process to be forced to converge to solutions that are also easily explainable. And this is something we have made a little bit of progress on. If you're interested, we very recently published a work where we use meta-learning to solve that. But the key idea is that you have a B-level optimization task where I don't know if you know a little bit about meta-learning, but the key idea is that you want to optimize a graph, in this case, a graph neural network. So you want to have high accuracy, but you also want that if I try to apply, I don't know, GNN explainer on top of that, GNN explainer should work very well. And if you put these two constraints together, you get a B-level optimization task where the inner loop is an explanation and the outer loop is the classical update of the parameters. And there are some libraries that allows you to solve this by linearizing the inner loop, basically. And it sort of worked very, very well. And we try it with both GNN explainer, PG explainer, plugging in a number of different things, and the explanations were almost always better. But again, the key point is that I think this will be quite interesting, because now we know how to make graph neural network or any kind of deep neural network actually. But in the real world, we need additional properties on top of those neural networks. So we want them to be efficient, we want them to be interpretable, we want them to be fast, etc., etc. And if we want those properties, we need to enforce them. So if you want the neural network to be as efficient as possible, for example, you need to train with some quantization, some sparsity, etc. If you want it to be interpretable, right now you have almost no leverage. So this was sort of a first step towards that. And okay, since we have a little bit of time, I wanted to show you some okay, I will be using PyTorch geometry. If you're interested, there are a lot of, the documentation is pretty good. They have dozens of good notebooks, but I made my own. Just to show you like end-to-end implementation, how that's not something we should have done. Maybe I made a copy, but it was not.
You're logged in as Michaelos.
No, I know, but it was supposed to be open to everyone actually, but maybe I made a copy by mistake and now I have to enable everyone. But this is pretty easy. Okay, now everyone can access it. I mean, since I also want to share it. So now, how do you increase the font size in? So let's and if you want to play with this, I will send you the link afterward, but no, it's too big. Okay. So the first thing you need to do is we need to install PyTorch geometric. It might take a little bit of time, but you see, just as out of curiosity, if you install PyTorch geometric, you also need to install a number of additional libraries, and the most important one is sparse. Sparse allows you to, has a number of highly efficient implementations of sparse matrices and matrix multiplications when one of the involved matrices is sparse. So those are the fundamental building blocks of any model in PyTorch geometric. And there's also this torch scatter, but this is mostly to do pooling and other things. So I will use PyTorch Lightning, which you might or might not know to do the training. So PyTorch Lightning is a very small wrapper around PyTorch that allows you to simplify a little bit the training. And I also use Captum, which is a nice library about explainability in general. So Captum was designed for computer vision, and it has almost every explainability method you can think of. I will show you how you can easily also apply it here by slightly modifying the methods inside. So, okay, but this is just PyTorch. I'm importing everything, PyTorch Lightning. I hope it doesn't crash. Because I have absolutely no idea why it crashed yesterday. So this is the dataset we will use. I was talking to you before. MUTAG is a kind of an hello world dataset for graph classification, and it's also useful in explainability because you know in many cases what the explanation should look like, because there are small parts of the molecules that are highly linked, are highly correlated with the classification. So if you know more than me about this, those are chemical compounds, and you want to predict if they are mutagenic on a certain organism, basically. So if they will have a certain effect on this organism. And so the input is a chemical compound, and the output is this binary prediction about the mutagenicity. It's easier to show it. So one of the things that PyTorch geometric has is a number of data sets, like in PyTorch geometric. So here I'm just downloading MUTAG and pre-processing it. And those are some basic characteristics. So this is the smallest. There are different variants of this data set. This is the smallest one, which has less than 200 graphs. Each graph can belong to two classes. So it can be mutagenic or not mutagenic. The feature, this has the number of features for every node. And the feature is a one-hot encoding of the atom type. So whether it's a carbon atom, a nitrogen atom, etc., etc. And there are also edge features that represent the type of chemical bond that you have, but we are not using them. So just out of curiosity, so the PyTorch geometric has its own data class to represent a graph. So one problem that you have in PyTorch geometric, standard PyTorch, everything is a very simple tensor. So it's rather easy to define data classes because you have vector, matrices, a rank 3 tensor, rank 4 tensor, but almost everything is rather easy to define tensor. With graphs, this is not so easy because every graph dataset has its own characteristics. You might have node features, you might have edge features, this might be point clouds, they might have locations, it might be bipartite, it might be a hypergraph, so it's a nightmare. And they try to do that using this data object class, which doesn't have a lot of constraints on top of that. So if you look at it, so the key point is that every graph dataset will have completely different features that you need to read about. In this case, it's quite simple because each graph has an X feature. So this graph has 17 atoms, and each atom has a one-hot encoding of its type. So this is the X matrix that we discussed before. And it has a single binary class associated to the entire graph, which in this case is 1. And just out of curiosity, Python geometric doesn't store the adjacency matrix as a big matrix, but in the coordinate list format we saw before. So you see the adjacency matrix, it's actually a 2 by n matrix, where every element here is the row and the column of the non-zero value of the connection. So basically, if you try to plot it, it will tell you, okay, there is a connection between 0 and 1, there is a connection between 0 and 5, there is a connection between 1 and 0, etc., etc. So this is telling you that there are 38 connections, and this is a symmetric data set actually, so there are 38 divided by 2 actual connections. There are some utility classes telling you whether it's directed or undirected. This is just for plotting. This is the actual compound plotted with the color corresponding to the node type. There's another one. Those are carbon rings, you see, and then here you have oxygen, and I don't know what this is. Chloro, okay. I mean, I really have an issue because I don't know about bioinformatics. Anyway, we're skipping a little bit this, but Python, if you know torch vision, you know a big thing inside torch visions are transformations. So you can normalize images, you can change the brightness, etc., etc. Python geometric also has a number of transformations that you can apply when you load the data set. For example, you can, in this case, I can transform the adjacency matrix in an actual matrix format if I need it for some reasons. So if I load the data set with this transformation, then I can also access the actual adjacency matrix in a matrix format if I need it. Or there are other interesting transformations. So for example, if you have a data set that doesn't have a graph, you can automatically build a graph on top of that by considering the distance between the points, like nearest inverse distance. Faster here. So once you have the data set, the first thing you do in classical PyTorch is you put the data inside a data loader to build batches. And Python geometric has a similar thing. So here it's just splitting in training and test. And then you have a number of data loaders basically inside, which are actually can be quite sophisticated because they can also implement sampling logic. So sampling a subgraph from a main graph, etc., etc. This is the simplest data loader possible, which just create a mini batch by, like I showed you in the slide this morning, creating a big graph with unconnected components. So here I'm saying, okay, build me a mini batch with a certain batch size of 32. And if I do that and I take a batch, what will happen here is that, you see now you have a huge amount of nodes, 578 nodes, but actually now those are the nodes belonging to 32 different graphs. So this is actually a huge graph made of 32 components, each one corresponding to a single molecule. I have 32 labels now because my batch is composed of 32 graphs. And those are the edges, so 2 times the number of edges. And these now edges will be actually the edges of all the 32 graphs. And there is an additional property that you can check that basically tells you for every node, I think this one, for every node, which of the original graphs it belongs to. So, for example, here this is telling you, okay, the first, you see all of these, the initial nodes belong to graph 0. Then, after a while, you get the nodes of graph 1, etc., up to 31.
I have a question for the batch. Because yeah, you say we put all the graphs into like one big graph, and like this with a batch. But why? So for example, for images, we're also not making one big images out of the other images in a batch. Why are we doing this for graphs?
Good question, because it's faster actually. Because the alternative would be making just it's not so hard to be, because since the key point is that in images, every image has the same shape. So it's pretty easy to vectorize on the dimension because you can just stack them together on a different dimension. And then everything works more or less easily, let's say. Here it's not so simple because different graphs have different dimensions. So it's not so easy to batch them on a different dimension, basically. Also, it depends a lot on the graph neural network that you're using, but it might create a whole sort of strange problems. So it's much faster to say, okay, who cares? Give me a huge graph, and I'm just applying my graph neural network on top of that. Imagine that you have like 5 nodes, 15 nodes, and I don't know, 1,000 nodes. If you batch that, you would need to batch with respect to the largest graph, and it creates. Then you need to mask. It creates a lot of problems. Other questions? So this is the interesting thing. Okay, so you see, this will be an integer from 0 to 31 for every node of this huge graph, telling you which original graph it belongs to. And you need that because you're trying to classify the graphs. So at some point you will need to average out the embeddings of each graph, not all the 32 graphs. And you can do that using some, if you remember, we installed also a library called torch scatter. And this is the kind of scenario where it's useful. So here we're saying, okay, give me a sum of the features, but sum them with respect to the integer containing this batch object. So basically sum only those of node of graph 0, sum those of graph 1, sum those of graph 2, etc. And the result you see is a 32-dimensional matrix. So one row for every graph with the sum of the features. Of course, there are also easier ways of in phylogeometric, there are also some let's say alias for making this easier. For example, there's global pooling, etc. Now let's see layers. Of course, you have layers. I just want to show you. I can use some. No. Okay. This is interesting because basically there's an by the way. So you see, phylogeometric is built around the idea of implementing message passing neural networks using this general idea that I described to you in the morning. So you define a layer by defining a function that builds the message, a function that aggregates the message, which is this square function, and then a function that connects this with the feature of the node itself. So this is the generic idea. And just to show you, for example, this is the graph convolutional layer that we saw in the morning. So this is Wx, there's a bias, and this is the weight, the normalized weight. So if you remember, we had d to the minus 1/2, a d to the minus 1/2, and this is the result. So you're normalizing by the square root of the incoming degrees of the two nodes. But again, this is AEJ in my slides. And this is the sum. So the way you would implement this inside Python geometric is to say, okay, so the input of a graph convolutional layer is x, and the adjacency matrix in the sparse format, so 2 times the number of edges. And the way you would implement the graph convolutional layer here, okay, here it just you add the self-loops. This part is the normalization of the adjacency matrix. We don't care about that, but you project the node features. So this is just a linear layer. And then you say, okay, propagate these messages here. And you just write out here. You just need to define what is the message, basically. And the message here is X times the corresponding element of the adjacency matrix. And once you do that, Python will automatically aggregate with the sum and do everything. So it's kind of really powerful. So again, you define graph neural network by just saying, okay, here's how you build a message, here's how you sum the messages, and here's how you combine everything together. If you define these 3 blocks, it will take care of actually propagating everything, summing, etc., etc. And there's an immense amount of layers that are already implemented. Here's a cheat sheet. But you see, they have a whole lot of strange properties, whether they work on sparse tensor, whether you can have a single scalar weight on the edge, whether you can have a vector of features for every edge, whether they work for bipartite graph, for static graph, lazy, there are other options, but you see you have GCN conv, which is the graph convolutional layer. You have other variants, but you also have GAT-conv, which is the variant. Actually, the one I show you is the GAT-V2-conv, which is likely better for some theoretical reasons. But you see, you have thousands of these variants. Some of them, you see, are for heterogeneous. There are also some variants for point clouds. Point clouds are just cloud of points without connections. A small amount for either graphs, etc., etc. Wait, I don't know. But see here, and they work more or less similarly to classical PyTorch. So I can instantiate a layer by saying, okay, I have 7 input features and 12 output features, where the features are the number of features for every node. And then I can run it just by passing X and the edges among the nodes. So the only difference with respect to classical PyTorch is you always need the features and the edges. So let me write the actual neural network. The neural network will be pretty simple because you see, I can just define one graph convolutional layer with 256 output units, another graph convolutional layer, and a final linear layer to make the final binary classification. So I only have 3 layers. And here's the forward. So I have my X, I have my edge index, so this is the adjacency matrix. Batch is the vector that associates every node to the original batch, to the original graph index. And so I just say, okay, I apply the first graph convolutional layer, redo, second graph convolutional layer, redo. I take the mean with respect to the original graphs. So the output here will be a 32-dimensional matrix. Then I apply a final classifier on top of that, and that's my output. Yes.
I noticed that the documentation of the graph neural network, they always consider the fact that node features exist.
Now you also have variants for only edge features.
Yeah.
For example,
Because I just checked the documentation, they give the edge feature as option, but they always consider that the node feature exists. What if I don't have node features?
That's a good question. So, okay, either it's pretty easy to let's say you can redefine everything in a dual format where basically the message passing is done for every edge by aggregating the messages for the nodes, basically. And there are some variants for that. So basically, you just translate the problem, every edge becomes a node, and you have the dual connections, and you can apply everything like here. But actually, you can also, for example, write a small layer that for every node aggregates the feature of the edges, and then continue from there.
I tried this solution by myself, but the results doing the transformation from edge to node representation.
Yeah, it's probably a poor idea. The best one, in my opinion, would be to you can do a graph convolutional layer where aggregate everything is done not at the edge level, but at the node level. So every edge, every node collects its edge features. But maybe it's better if I write it out afterwards. But yes, I mean, almost everything right now is implemented for, node feature and maybe node plus edge features, but nothing in the framework is like specific for that. So you can also implement layers that only takes edge features. It's not, you can do that inside the framework because these inputs are not standard. So you can have any inputs you want, and the dataset can have any property you want. So you can define a dataset where you only have edge features, and graphical networks that only. But actually, I can show you. Sorry, I'm very bad here. No, I just wanted to show you that
I can create my own dataset and change it.
Because there are some datasets that are defined for a point cloud. Now, point cloud are just clouds of points with their spatial coordinates.
Okay.
And
data, on the left. Torch geometric on data.
Yeah, but if you look at the way they're defined, sorry, no, that's the paper.
Torch, yes. You will find it in Torch geometric dot data.
No, I want something else. So basically, let's see if they have the equations here. Here's the equation. So basically, those are defined with respect to you see that it's a summation with respect to differences of the features, for example. So actually, the summation is made with respect to the edges, but with some edge features, actually. So this should be relatively easy to adapt to. Or another alternative is that you manually add node features. So for example, one simple thing you can do is that if you read the paper this morning, I suggest you to read this paper because there are many different ways of adding, you see, positional and structural and node features inside. Basically, for example, you can take the Laplacian, you do the eigen decomposition, and you add the first k eigenvectors as node features.
Okay. For me, initially, I tried to extract some node features to be able to use the predefined functions in PyTorch, and I used the edge feature as an option. But it seems that the model is giving more importance to the node features.
Faster.
Okay.
Anything else? Okay, this is the model, so it should be rather easy to understand. So those are standard graph convolutional layers. This is just an activation function. Here I'm taking the mean. The only difficult part is that I'm taking the mean with respect to every graph. So this is a huge graph made of 32 different disconnected components, and here I'm taking 32 different means by giving it this batch which associate every node to the original graph, and then I just do a final classification, so I will have 32 scalars. If you have never used PyTorch geometry, it's just a wrapper around PyTorch. I just need to specify the training step. So the training step, it's classical because I'm just saying, okay, give me my prediction, compute the binary cross entropy, and that's it. It's a standard classification loop. And wait, let me run it. I'm instantiating it. This is just a signity check. So you see I get 32 outputs, scalar outputs, which are the binary classification. I can define some callbacks like in Keras, if you're used to that. I instantiate a trainer with a certain number of epochs, and then I can just run the fit option. And so you see I have 3 different layers, certain number of features. This is the most big network. I only have a small number of output classification feature because I'm just classifying from 256 to a scalar, and it's pretty quick. You see, I get a very high training accuracy almost immediately. Let me stop it, it's going too fast. Okay, I mean, I could try it out, but I wanted to show you something about explainability. Still have 5 minutes. So here's an example about explainability. So I'm taking the first graph in my test data set. Okay, this is a molecule, and this molecule is mutagenic. And actually, phylogeometric has its own variant of, GNN explainer inside. We can just wanted to show you the implementation. Who knows where it is? You can read the source, it's pretty easy, but basically, you see it's initializing some masks. So here's the edge mask. So it's a parameter, it's a mask with respect to the number of edges that you have in the graph. And then when you say, okay, explain this graph, what happens is that there's a small optimization loop here. And inside the optimization loop, you are masking the X, so X time the current node feature mask. You're masking the edges. It's above, and you run the model, and you compute the loss. And if you compute the loss is just, I lost it. Cells get lost. Oh, here. You get the edge mask. So you see, you have, let's see, not easy to see it from here, but basically, this is sort of a cross entropy between the current log hits and the prediction. Then you have this is the L1 part here. And this is the entropy part. And you sum all of these together, and you get the loss, and you iterate until you have the final mask. You can try that. So you can initialize GNN explainer and say, okay, explain this particular graph here. It will run the small optimization loop, and I can get the result. So I have a feature for the edges, a mask for the edges, and a mask for the features. There are 42 edges here. I can just threshold the mask. So I say, okay, give me all the weights above 0.8, the most relevant ones. And then I just basically plot here the final graph. And you see, it's pretty good because those are the two NO2 triplets that were the most significant for this mutagenic part. And if you want, here, I'll stop, but I also have an example of how you can use integrated gradients here. So you see, you initialize, this is from Captum actually, from the Captum library. sort of works. So this is the result of the integrated gradient. So basically, like before, like I told you, it will integrate the saliency maps from the zero gradient to zero graph, let's say, to the full graph. And you see it sort of works well, but it has a number of additional unwanted things on top of that. So I also wanted to add the input saliency, but I got lost and I didn't have time. And also, it's over. So I will. You will find this at the end in the slides, and I mean I hope it's documented enough. But if you don't, you find something strange, just write it to me. And I also suggest you to check the actual notebooks from Python Geometric because they're decently good. And so I want to thank the same exact people I thanked this morning. So also thanks to you for listening to me for 4 hours.